Hey guys, and welcome back. My name is Savannah. I'm an application specialist here at Thermtest. Today, in this two-part series, we're exploring nanotechnology in a unique way. We're going to measure the impact of nanoscale and trapped oxygen on the thermal conductivity of 3D printed metals. We are here to demonstrate this in the Applied Nanotechnology Lab at the University of New Brunswick, one of our customers. Joining us for a moment is Dr. Felipe Chibante, the Nanotechnology Chair here at the University of New Brunswick, to share a few thoughts on this area of research.
Hello, I'm Felipe Chibante. I'm a professor in chemical engineering at the University of New Brunswick. Part of our lab is we look at materials properties, in particular for things like mechanical properties, thermal properties, etc. And we have a strong focus on thermal properties. For example, this is why we like to use the Thermtest transient instrument. For example, the putts you may have seen earlier, these are actually 3D printed materials, and thermal properties is an important part of their utility. And so we found that depending on how these are made, their thermal properties can change. So if you're looking at a heat sink application and you're 5 to 10% off, that can have a big impact on thermal properties. So we're very impressed with being able to look at these properties at a very detailed level, at a high reproducibility and very excellent precision. And so we're hoping to explore these even further as material science keeps to explore the boundaries of nanotechnology.
In part one, our focus will be on measuring the thermal conductivity of a few common solid metals used in 3D metal printing. We will be testing these samples using the MTPS sensor available on our advanced MP-1 platform. The Thermtest MTPS sensor is able to measure the thermal conductivity at different timescales, investigating metals for homogeneity. Stable thermal conductivity at different penetration depths would suggest that the sample is homogeneous. Before we delve into our experiment, let me provide some background. The MTPS method following ISO 22007-7 enhances the standard TPS method by allowing asymmetric testing with just a single sample piece. This innovation is crucial for materials with unconventional shapes or limited availability. The Thermtest MTPS offers distinct advantages over ASTM D7894, providing absolute multi-thermal physical properties and versatile testing modules like anisotropy. The MTPS sensor covers a broad range of materials from 0.03 watts per meter Kelvin to 500 watts per meter Kelvin, making it ideal for diverse applications. We'll start by walking through the basic setup of the MTPS sensor. So here we have a solid sample of stainless steel 316 that we're going to be measuring with the MTPS sensor. So to set up a measurement with this sample, all you would do is set the sample directly on top of the sensor, making sure that it's centered. And then you would apply the provided weight to ensure good contact between the sample and your sensor. And that's all there is to setting up the solid steel sample. So now we will move to the software where we can set up our schedule. So now in the scheduling page of the software, we can select the method that we are using. So using the MTPS sensor, we will select the modified 3D disk source method, isotropic and infinite. Then you can enter your operator ID and select a save location. Moving on to the sample page, you can input your sample name. So for this measurement, we'll be running solid stainless steel 316. For the testing port, we have the MTPS hooked up to port 1 of the MP-1. So when you select the MTPS, it will autofill your backing material. Next, we can input the sample height, which we measure to be 12.7 with a radius of 25.4. Next, we can check the resistance of the sensor. Perfect. So moving on to the schedule page, you can click this little plus button to add a new schedule line. Then we're going to select the ITPS to help optimize our test parameters. So ITPS is our Intelligent Transient Plane Source Parameter Selection Tool. So when we click this, we can see that our test time and power is optimized. So as a user, all you have to input is the sample name and dimensions, and ITPS will run a short measurement and then provide the optimal test time and power to use for the most accurate results. I'm going to leave the number of tests as 5 and a delay of 10 minutes in between my tests, and then click Start to begin a measurement. And now we can move on to analysis. Here, we present the results of measuring solid stainless steel and titanium samples using the MTPS sensor. We conducted measurements at various test times and plotted these against the corresponding probing depths for each sample. The data indicates that as the test time increases, the probing depth also increases. The optimal test time, as identified in the second data point on the chart, provides the most accurate measurement. The intelligent transient plane source function evaluates and selects the ideal test time for each material, ensuring that heat remains within the available penetration depth and providing the most precise measurements of the samples. Along with patented advancements, we continue to strive for the intelligent MP-1 to be the apex of thermophysical instrumentation. Stay tuned for the testing of 3D printed parts in Part 2. If you have any questions or if you want to see your own demo, please contact us at info@thermtest.com or with the information, click the link in the description.